we define a property as a measurable macroscopic characteristic of a system. We are only looking at macroscopic thermodynamics. So, these are all our properties are macroscopic characteristics, but more importantly thermodynamic properties relate to energy. So, we said that thermodynamics is a science which deals with conversion and transformation of energy. So, we are interested in properties which deal with energy. Some examples of those are given here, for example pressure, temperature, volume and so on. We will look at several other properties like enthalpy and entropy and so on as we go in this course, but for the time being we are just sort of limiting ourselves to these three. We have a further classification of these properties as extensive, intensive and specific. So, extensive properties depend on the extent of mass, or the value of the property depends on the extent of mass. Intensive properties are independent of the quantity of mass, and a specific property is an extensive property which by some means we make independent of the quantity of mass. So, let us look at an example of all of these. So, let us say I have a box which contains some mass. So, if I cut this box into two, does the mass of each, so this has some mass m, if I cut it into two equal parts, does the mass of each part change? So, if it changes, then that is an extensive property. So, the mass of each part does change. So, mass itself is an extensive property. Let me see volume. So, this box entirely had some volume. When I cut it into two parts, each part has a volume which is different from the initial volume of the entire full box. Therefore, what we see is that volume also is an extensive property. So, let us say I was measuring temperature. Initially, the temperature everywhere in the box was uniform. I was measuring it, I had some value. I cut it into two parts, hypothetically cut it or put a partition and cut it. Does the temperature of these two parts change? We do not expect the temperature to change. Therefore, temperature is independent of the size of this box or the mass of this box, and therefore, the temperature would be an intensive property and so on. So, similarly, if I take this marker, it has some temperature, I can put like 5 thermocouples and measure. Let us say all of them show me the same value. I cut it into 5 parts. I would expect each of those parts to still have the same temperature. So, what I see is temperature does not change depending on how much of this quantity of this system I take. If I make the system into half or into 3 parts or 4 parts, it still is the same. Therefore, it is an intensive property. So, we have extensive properties like say mass, volume and so on. We have intensive properties like say temperature. Pressure is also an intensive property. If I measure the pressure at different locations on this and it was the same, if I cut the box, the pressures would still be the same. So, therefore, it is also independent of the mass and therefore, it is an intensive property. So, I have for example, pressure, temperature. Here I have for example, volume, mass and so on. Since I have this volume which is an extensive property and we do not usually like to deal with extensive properties much. So, is there a way of finding out some volume which does not depend on the quantity of mass? So, a way to do that would be I take the volume, I divide by mass and then this becomes something which is no longer dependent on the quantity of mass. So, that is something which we call as a specific volume. So, V is what we call a specific volume. Similarly, I can find other properties on a specific basis. We will see that later on. We will see that energy is a property. We can have specific energy. We can have enthalpy, which is property. We have specific enthalpy. We have specific entropy and so on. So, we usually use some kind of a system to denote these things. So, for extensive properties, we usually use capital letters. So, for example, V denotes extensive property. There are of course some exceptions which you already see. We use small m for mass because we use capital M for molecular weight. We use capital T for temperature, which is an intensive property because we use small t for time. But for the other things, so you will see that we use small letters usually for intensive properties. So, small p is pressure, which is independent of the amount of mass. So, it is an intensive property. For specific properties which are also independent of the mass, we use small alphabets. For example, we will use small v for specific volume, we use capital V for total volume. So, if I was to remove the exceptions over here, what we see is that we use, for example, small v, small p and so on for things which are independent of mass. We use capital alphabets for things which are dependent on the quantity of mass. As I said earlier, temperature is an exception because small t is you generally use for time. We do not want to use the same alphabet for multiple things. We have what is called as a state, which is a set of all properties required to completely describe the system. So, we can think of this as somebody asks you where you are, you need to give them information so that they can find you. So, you need to give sufficient information. So, similarly, in somewhat similar fashion, we can think of a state as all the things which you need to tell so that somebody can reproduce exactly the same system which you have if they want to get there. So, for example, you have air in this room. If somebody needs to recreate this room, they need to know what is the air, what is it composed of, what is the temperature, what is the pressure, is it moving and so on. So, all of the properties required to describe the system together is what is called the state. Since we are trying to define the properties, it means that the properties should not be changing, because by the time we measure it, it should not be some other value. So, we need the properties to be constant, or at least we need to be, if it is changing, we need to have any changes. So, be so slow that we can sort of specify that about this time the value is this. So, after a day maybe the value is something else, but at least today or at least at this point of time it is like this. After 1 hour it may be slightly different, that is all right. And in order to measure, since things should not be changing, we need the system to be in equilibrium, which means things should not be changing, because when it is in equilibrium the properties have definite values. And any two independent properties can be used as axis and the state can be plotted as a point. So, we are used to, for example, plotting graphs of say y versus x. So, if I tell you that some distance in y is 2 centimeters and some distance in x is 2 centimeters, so you can plot it and say that this represents that point where y is 2 and x is 2. In a similar fashion, we can plot various properties on graphs, and they are useful because they help us to visualize processes which happens. We can plot any property versus any property. Which set of graphs we use depends on what we can see from the graph. We would like to plot something which shows us something. So, for example, if the temperature is a value of say some 300 degrees centigrade or 300 Kelvin or something like that, and my volume which I have is like say 5 meter cube. So, I can plot this point and say this represents my state as far as temperature and volume are concerned. So, I can plot this. If the state changes after some time to some other value, I can also plot that. So, similarly, I can also plot, for example, pressure versus volume. And I can show what happens when the pressure changes or when the volume changes. One example I can think of is I have a bicycle pump and I am filling a tire of my cycle. So, initially the pressure inside my bicycle pump is low and the volume is high. Then I press the plunger down. Let us say for the moment I keep the outlet closed. Then as I press it down, the plunger down, what I see is in my bicycle pump the pressure increases and the volume decreases. So, I can plot this on a curve. So, initially let us say my pressure is 1 bar, my volume is some 5 units of something. After a while, the pressure, when I press it down, the pressure increases, which means the new point must be higher on the p axis than this point, and the volume reduces, which means the new point must be closer on this side. So, finally, maybe I get some point somewhere over here. So, this is my initial point 1 and this is the final point there. So, I can plot these kind of things on these graphs. So, we also have what is called as a phase, which is a quantity of matter which is homogeneous throughout. So, we talk of, for example, a solid phase, a liquid phase, a gaseous phase for the air around. We can also talk of plasmas. In solids, we can have various different kinds of solid phases, but for the purpose of this course, we are just interested in like a solid phase, a liquid phase and a vapor phase, and we will look at some changes in phase between these. And then we have what is called as a path, which is the locus of all the intermediate states which the system passes through when there is a change of state. So, for example, we just looked at on a PV diagram a case where I have a bicycle pump, for example. I start, it has some volume and some pressure. I press the plunger in. After some time, it has some other volume and some other pressure. This is the initial state, this is the final state. But if I do this process really slowly, I can also measure all that at any time in between, how this is varying. So, I can measure after some time, maybe it is here, after some other time it is here, some other time it is here, here, here and so on. And then I can connect all of these. And if I connect all of it, that is what is essentially called as a path. It is a locus of all the intermediate states which the system went through between the initial state and the final state. And whenever there is a change like this, we say a process occurs. So, a process occurs when a system changes from one state to another. So, when I look at this, some process has occurred where it went from some volume and some pressure to some other final volume and some other final pressure. In a process, anything can change. For example, the pressure can change, the volume can change, the temperature can change, mass can change and so on. But there are some special processes where some property remains constant. So, if I take a system, then by definition the mass is constant, because when I talk of systems, I am generally talking of closed systems. So, the mass is constant. If I have some mass of say gas in a rigid chamber such that the walls of the chamber cannot change, then for example, I have a process, whatever I do to this, the volume is fixed. So, it is rigid. So, the volume is constant. So, such a process is what I would call as an isochoric process, where volume is constant. Similarly, I can have some other process where the pressure is constant, and that would be what we call as an isobaric process. So, a process where we have the temperature constant is what we call as an isothermal process. So, these are all special processes. A process where there is no heat transfer, properties change, that would be called as an adiabatic process. It has a separate name, but of course, nothing is constant in that, in this fashion. Then we have what are called cyclic processes, which we will come to. And in order to define state, we said that you need to have equilibrium, which means things should be constant as a function of time. So, in order to have equilibrium, we say that you should have mechanical equilibrium, which is that all forces must be balanced. You should have thermal equilibrium, which means there should not be any difference in temperatures. You should have chemical equilibrium. If there are reactions, rate of forward and reverse reactions should be the same. You should have phase equilibrium. So, if I have a mixture of two phases, for example, water and ice. So, whatever is the quantity of ice and the quantity of water, they should be constant. There should not be net melting of ice into water or net freezing of water into ice and so on. So, that is phase equilibrium. And in order to have all of these and still have some change, we talk of what are called quasi-static processes, where a process is always near equilibrium and anything which changes so slowly that if you look at it, you can assume that it is always under equilibrium. So, we are going to look at a few of these things. So, we look at first a cyclic process. So, let us say you have a piston and cylinder. So, this is a piston, this is a cylinder. This is usually our most favored configuration for describing a lot of things. We will keep going back to piston cylinder arrangements. So, it has some pressure and some temperature and volume. We call that as state 1. Very slowly the piston and cylinder arrangement, the temperature inside this, let us say, changes after some time. So, this process is happening slowly, then we call it a quasi-static process, and after some time the temperature here is something else. So, it is now in a new state because things have changed, properties have changed. After some time, let us say I pull this piston down, the volume is increased, temperature also might have changed, the pressure also might have changed. This is some other state 3, and after some time something else has changed. I come to some state 4, maybe the temperature has changed or pressure has changed again, and after a while I change something else so that it comes back to whatever the set of properties was initially. So, it comes back to state 1. So, I started from state 1, I did some lot of stuff, I came back to state 1. So, this kind of a process where we reach the initial state, is what we call as a cyclic process. So, the final properties there are the same as the initial properties which were there. So, if initially the pressure was P1, finally the pressure is again P1. So, if I want to find out the change in pressure, it is essentially 0, because initially let us say the pressure was 1 atmosphere, finally the pressure is 1 atmosphere. If the change in pressure between the first state and the last state is essentially 1 minus 1, which is 0. Similarly, change in mass is 0, change in volume is 0, change in temperature is 0, and so on. So, there is no change in any property between the initial and the final state. So, I can look at the same thing, for example, for this marker. So, initially it is sitting somewhere, I slowly lift it up, I bring it here, its state has changed because it is now sitting in a different position with respect to the earth. I slowly put it back where it was. Once it is back in the original place, I have done this process very slowly. I measure the temperature, it is still the same as it was initially. The pressure is the same, its potential energy is the same, its kinetic energy is the same, and so on. So, essentially the state would not have changed if I took it up slowly and brought it back and kept it slowly in the same place. So, these are essentially cyclic processes. We said that there has to be equilibrium in order to measure the properties. So, we said there has to be thermal equilibrium. So, the reason this has to be there is that if I have a box like this where one side is hot, the other side is cold, and if I want to tell you, measure the temperature and tell me what the temperature of this box is, you may not know where to measure. For example, if you measure somewhere here, you will get a higher value. If you measure somewhere here, you will get a lower value. So, we are not able to find out a single value which is representative of the temperature of this entire box. Whereas, if we leave it for a while, after a while the temperature inside will be uniform. Now, if I ask you, tell me the temperature of this box, you can measure anywhere. You can measure here, 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 it does not matter. Anywhere you measure, the value is the same, and you can tell that this is the value of temperature for this system. So, what we are looking for is for systems under equilibrium or very close to equilibrium, so that we can define the properties of this system. In a similar fashion, what we see is that we need to have mechanical equilibrium. So, if I have this piston cylinder arrangement again, if I was moving this piston really fast, either down or up, then the pressure near this piston and the pressure far away from this piston would not be the same. Because this is moving really fast, the pressure here would be lower if it was moving down, and the pressure there would be higher. Then if I ask you to tell me what is the pressure of the system, you would say, okay, at the top it is this value, at the bottom it is this value, I do not know what is the average pressure. So, that kind of a system is not very useful because we do not know how to deal with it. Whereas, if this is moving slowly or if it is stationary, then everything inside is essentially the same. The pressure at this point or some other point here or some other point here or here would be the same or approximately the same if it is moving very slowly. Then what I can say is, I can say any of those is representative of this system. So, we are looking for systems which are close to equilibrium even if they are changing, or at equilibrium, then we can define the properties very clearly. So, it is those kind of systems which we are going to deal with in this course. So, we say quasi-static, near equilibrium processes we can deal with efficiently. So, that is essentially where I am going to stop for this class, and we will continue with parts independence and path dependent quantities, or essentially exact and inexact differentials in the next class. Thank you.